Here is this Tepee simulation code where we use the algebraic method to solve it. In this video, we're going to rewrite the code using Newton's method, just replace the parts we need to, and it should look exactly the same with the numerical solution. So we have velocity, position, and the actual now flattened Tepee. So we've got the equations here that we're going to need. The main things we're going to focus on are the position equations that we got from the vector loop and the Jacobian. We're going to replace our algebraic solution, which here, line 31, we calculated the unknowns using a function, solve Tepee. And you can see that solve Tepee function over here in our current folder. Well, if we're going to solve this numerically instead of algebraically, we're going to use Newton's method of guess and check. And so instead of calculating the unknowns with this solve Tepee function, we're going to put the calculation actually inside of the for loop to get our R1 and T3 unknowns. So let's first fill out with comments the way that we're going to program this, and then we'll put the math in underneath the comments. So we'll delete that. Now, the first thing we're going to do is take that for loop, and we need to calculate the unknowns inside the for loop. So we'll put it there. Now, the way that Newton's method works is if you have a function that you want to set equal to 0 and find the guess that makes that equation true. So let's go over to the whiteboard and just kind of refresh on that. So if we're given a function f of x equals 0, and we want to solve for x, if f of x is some really complicated thing that we can't just directly solve for x easily from, we'd have to guess what x is and and then check to see if that was right. Does f equal 0 without x? And if not, we guess again, and so on. So Newton's method actually does this in an organized iterative fashion. So first thing you do is guess. So you want to guess a value for x that is reasonably close. For something like angles in a vector loop, you want to get your quadrant right. Or sometimes, if the angle is straight up or down or straight to the side, you want to bias it a little bit in the direction that your linkage is going to move. So you guess x, and then you calculate f. And then you need to see using that x. So guess x in, it's a number that we've guessed. Calculate f in, and then you want to see, does it equal 0? So if it does equal 0, then you can stop right there, you found it. If it doesn't equal 0, you need to re-guess. So new guess is going to be x in plus 1, the next number, equals the old x, x in, minus f of x in over f prime of x in. This is the derivative. So that's how it works for scalars. But what we had is the Tepee, which we'll draw here. We had, this was R1, R2, R3. And so our equations are F, I guess, well, let's see, we had knowns, which was R2, R3, theta 1. We had the input, which we said was theta 2, and then we had the unknowns, which were theta 3, R1. And we had our vector loop equation, which if we go counterclockwise around the loop, R1 minus R2 plus R3 equals 0. And then we split those up into our X and Y position scalars. X, Y. And our X1 is R1 minus R2 C2 plus R3 C3 equals 0. And our Y equation is negative R2 S2 plus R3 S3 equals 0. Okay, and you can review those in the previous video. Click the link up here. So we need to take these and put it into this new guess type of form. So we need to figure out what is F prime, and what is X. So X is the unknowns. So the X vector really is going to be R1, theta 3. And then the F is going to be the X and Y, because those are the equations. We want the vector loop to equal 0. So F is going to equal X, Y. And then F prime is really the Jacobian. And from our previous video, we know that the Jacobian is going to be just a partial derivative matrix. So we will have the X and the Y components here, and the R1 and the theta 3 components here. So J is going to be a 2 by 2. So we just look for the coefficients of R1 and theta 3 from the velocity equations, or the partial derivatives of R1 and theta 3 from these X and Y. So that will be 1, 0 for R1, and for theta 3, we'll have negative R3 S3 and R3 C3. Okay, those are the partial derivatives. For more details on how you get those, look at the JVA math video, click the link up above. Anyway, now we've got what all of these things are, and we just need to go over and put them into Matlab. Back here in Matlab, let's put that up here just as a reminder for ourselves. And now we'll fill in how we actually calculate these unknowns. So first thing we want to do is calculate the vector loop position scalars. And then we need to find the error, because we need to check, do those position scalars end up equaling to 0? And then if they are not equal to 0, we need to do the guess and check. So that'll be while error is greater than tolerance, we'll do our calculations, and then we will save the answers. So doing the calculations, now in here is where we calculate Jacobian. And then we will need to make our new guess. And then again, we will recalculate position and recalculate the error. Okay, so the Jacobian, actually we have already, we did it down here. So let's just take this and put it in here. Now, starting back up here at the top, calculate vector loop position scalars. Those are the X and Y equations, so let's just type those in. All right, now here, we have indexed correctly, except actually we'll need R1 of count. But really for this, we don't know what R1 and T3 are yet. We still have to calculate those. So how do we calculate the error without knowing what those unknowns are? We have to guess. So that's back with figuring out our first guess. We need to go up here and make initial guesses. So when we start, the TP is completely vertical. So if we look at this picture over here, when the TP is completely vertical and R2 and R3 are touching at both ends, R1 is going to be about 0, and R3 is going to be about 90 degrees. So let's make those guesses here. R1 guess equals 0, and T3 guess equals pi over 2. Okay, and then we need to pre-allocate some arrays for R1 and T3. So R1 equals 0s and 1, T3 equals 0s and 1. Okay, so now we'll define the guess vector. We have to take those R1G and T3G and put them inside of a vector called guess. This is a column vector, and if you go back, that's because looking at this theta dot, or even if we go back to the whiteboard, R1 and theta 3, xn is our guess. So we have to put those two things in a guess matrix. Just like we need to put actually x and y need to go into a matrix called F. So we'll go back to Matlab. So x and y, now we're going to replace these. R1 is going to be R1G. And then T3 is actually going to be T3G because we're using our guesses here. And then we'll define F equals X, Y, column vector. And then the error is going to be the magnitude of X and Y. So like if X and Y are the two sides of a triangle, error is the hypotenuse. So that is the square root of X squared plus Y squared. Now, there's actually an easier way to do this. We just need the magnitude of F, which is, again, the hypotenuse of that triangle. So what we can do, instead of typing out square root X squared plus Y squared, for example, if F had more than two things in it, like you need X squared plus Y squared plus Z squared and so on, it just gets to be a lot to type out. So there's another function called norm. We'll just say norm of F. And that way, no matter what size matrix F is, then it will still be able to calculate. It does the same thing of square root sum of the squares. So, okay, we've got that. So then while error is greater than tolerance, then we need to define a tolerance. How close is close enough to 0? It kind of depends, what magnitude of things that you're working with. But if you look here, R2 is about 10. We said TP length in feet. So maybe we'll say that our tolerance equals 0.0001, 0.01. They're 1,000th of a foot. That's probably close enough. So we'll put that there. The bigger your tolerance is, so like the fewer 0.0s you have in there, then the faster your code will be able to calculate the correct answer because you gave it a bigger window of what is an acceptable answer. The smaller you make it, the more accurate it will be, but the longer it will take to calculate. So usually something like 10 to the minus 3 is decent. Okay, so now back down here for our new guesses. So if error is greater than tolerance, it's going to enter the while loop, calculate the Jacobian. Now we need to calculate that new guess. So the new guess equation is guess equals the original guess minus that correction factor, which is inverse Jacobian times F. Now you can see the INVJ is underlined. It says this is slower and less accurate than a backslash. So we can just do J backslash. Both ways work. So just to be clear, both ways are fine. But since MATLAB prefers J backslash, we'll just put that and make it happy. Now you can see the square is green again. Okay, so once we've got those guesses, but now we need to tell it which part or which element in guess is theta 3 and which element is R1. So the way that we've defined it here is R1 is on the top, theta 3 is on the bottom. Same thing here, R1 is on the top, theta 3 is on the bottom. So we're going to stick with that for this, and R1G equals guess of 1, first element, and T3G equals guess of 2, second element. Okay, so then recalculating position scalars in the error, those will be exactly the same equations that we've got up here. Now there's one more thing in this while loop we need to fix, and that is here, the T3 of count needs to be T3 guess. Since we're using the guesses everywhere, we just need to be consistent. And then we need to, once we figured out the correct value, so once the error is small enough within the tolerance, the while loop will exit. So it gets out the while loop and we need to save those correct answers. So we'll save them in the array that we pre-allocated. R1 of count equals R1G, and T3 of count equals T3G. So it's green, MATLAB is happy. Let's run the code and see if this works. We got an error. Unrecognized function or variable J. How did J? Okay. So what happened here is it actually skipped the while loop. I'll run the code and we'll stop it here. So let's check our error. Error is 0. That's because our initial guesses were correct. They were absolutely correct. And so it never went inside of the while loop. So we actually need those guesses to be off just a little bit. Now, looking at the TP, as the TP opens, theta 3 is going to start at, it starts at 90 degrees when the TP is vertical. And then theta 3 is going to increase. So let's bias it a little bit to make sure that the TP opens towards the right side instead of towards the left side, because if it starts right up, MATLAB's not actually really going to know what to do. So let's make theta 3 a little bit bigger than 90 degrees so it knows which direction to go. So maybe we say pi over 2 plus 0.1. Okay, so now we should get an error. So we'll quit debugging and run. Good, here it goes, got through that all smoothly. All right, so looking at this acceleration graph, you can see that it does some mighty wild spikes over here on the end, and that is when the TP is just starting. So theta 2 is 1.57, about 90 degrees. Those wild spikes happen because it begins in a singularity configuration. And let's check velocity. Yep, got some weird spikes there. So what we can do to kind of avoid all that is we'll start not in a singular configuration. So instead of starting at 90, let's start theta 2 at 89 degrees. And then that should mitigate some of that. Okay, so you can see that's much smoother. still got some steepness, but it's a whole lot more believable than those first graphs. And that's because of that singularity there. Now, the thing we forgot to do was to rename this. So our original algebraic method was TP simulation. This one we should have probably renamed, since now we just overwrote everything that was on our old code. It's good practice to rename something if you're going to be making any major changes. That way you have the old one to go back to. So this works, it's okay, but just in case your Matlab skills are not super confident, you want to save and rename. So we'll call this Newton, TP simulation Newton. There, now we have it saved as the new one. Normally you'd want to do that at the beginning before you make your changes. And those .asv files, you don't need those, you can delete them. Okay, so no warnings found. Code looks good. This is how you use Newton's method instead of an algebraic method to solve and plot a vector loop.